Good morning, and welcome to routing lecture number 4. Routing and addressing, really. Okay, so quick. Today in computing, February 13th. 74 years ago was the first demonstration of ENIAC, which was the electronic numerical integrator in computer. It was really the first real programmable electronic computer. I think it was today. There seems to be some disagreement on this subject. The actual dedication of it is the 15th, and there's a lot of people who mention there being a demonstration on the 14th, but there are also some references to there being a demonstration late at night on the 13th. So I think maybe today. It was designed at University of Pennsylvania. It's still there, or at least part of it is. In fact, the part that you can see in this picture, I think, is still there. If you visit UPenn, you can go look at it. And so, yeah, there's a picture of part of it. The whole thing was much bigger. I think a lot of it has been lost at this point. Those are two of the original programmers of it standing there. So it had 20,000 vacuum tubes and drew 150,000 watts, so something like 3,000 times more electricity than your laptop. So ENIAC's birthday-ish. It's also the birthday of William Shockley, who's dead now, but in 1910 was born on this day. He was a major player in the development of the transistor. He won the Nobel Prize for it along with a couple of his colleagues at Bell Labs in a lab that he directed there. So he, to commercialize the transistor, moved from New Jersey to Mountain View, and this was the first semiconductor company in the Bay Area. This was the beginning of the Silicon Valley, was him. So just to pull things together, last time I mentioned Mike Markkula, who I mentioned worked at two companies, Fairchild and Intel, before he worked for Apple. And before that, talking about Jack Kilby, who invented the first integrated circuit, and then the guy who invented the second integrated circuit was Bob Noyce. Bob Noyce also worked at Fairchild and Intel, was a founder of Intel. But before that, he worked for Shockley. And he and 8 others rebelled, left Shockley, started Fairchild, then he left Fairchild and started Intel. So all of this ties together, the Silicon Valley history here. All right, so today in 168, gonna do a project update. Going to finish up talking about learning switches and the spanning tree protocol. Then going to talk about addressing. And then if we have time, which I don't think we will play the spanning tree game. So starting with that first one, an introduction to Project 1 by Lloyd, who is the lead TA on that project. Maybe this will work.
Is this working? Can you guys hear me? Okay. Okay, so today we're releasing Project 1, like the announcement I sent out last night. It's going to be about distance vector, so you're going to be implementing a variant of distance vector. Just a couple logistics-related things. I sent in a post on Piazza detailing... can you guys not hear me? In the back? Okay. I'll get close. So we put up a post on Piazza detailing where you can find all the project-related materials, which includes a write-up. Please go through the write-up as you're doing the project. It will help you immensely. Also, we have worked hard to put a bunch of demos in place that allow you to see what's going on with your router on a bunch of different topologies. Please go through the demos for each of the stages as you're going through the project. They'll help you not only understand what's going on in the project in total, which will help you get a better grade on it, but it will also help you for the exams, too, to understand how to implement distance vector. A couple other things. So on Piazza, we will be, of course, you guys answer or ask whatever questions you want if you have questions about the project. We will be doing all setup-related things on Piazza. We will not be doing any setup, like installing Python and all that kind of stuff, in office hours. Lastly, regular office hours should not be used for project-related questions. Those should all go to our new product office hours, which are now updated on the course schedule. If you have any other questions, please feel free to either ping me on Piazza or the other TAs and come to office hours, and we can work on distance vector. Okay, thank you guys.
Any questions for Lloyd right now, off the top? All right.
Thank you.
right. So, learning switches and the spanning tree protocol, which is where we left off last time. I'll sort of recap where we were, which was getting through most of learning switches, and then we'll move on to the spanning tree protocol. All right, so we've been looking at distance vector and link state protocols where the tables are kind of filled in by this ongoing routing process, right, with these like ongoing, routing messages. And for both of those protocols, we sort of seeded the routes with, like static routes, which then got sort of propagated. And these two types of routing protocol are really common for working with L3, for the network layer, with IP addresses. And then we decided we're going to look at something really different, which are learning switches. And in those, the tables are filled in sort of opportunistically by the data packets. There's no separate routing packets that fill in the tables. And there's no seeding with these static routes. And these are really common to do essentially routing at L2. Some people won't call that routing, but it fills in the tables. So I'm going to call it routing. The way it works, really quickly, is that when a data packet arrives at a switch from some neighbor, like here we're showing a data packet from A to B arriving at the switch S1, when that packet arrives, you know that you can reach the source of that packet by following that packet backwards, right? If you use the neighbor that you got the packet from, you should be able to get to the source. And so we use the source address in the packet to fill in a table entry for packets destined for that address. So in this case, that's A, so we populate the table entry for A at S1. Now this packet is going to B, and we don't have a table entry for B. And so in everything we looked at so far, when we run into this case, we would just drop the packet. We'd say we don't have a table entry, we don't know what to do with this. But what we do here is instead we flood it. We send it to all of the neighbors. It's sort of, we're being optimistic that B is out there somewhere, and if we just kind of send it to everybody, then it'll get there. So S2 and S4, at this point, see the packet, and they say, well, it came from A, and it came from S1, so I should be able to reach A through S1, right? They also don't know what to do with the packet from B, so they flood it. So S3 learns that it can reach A through S2. S5 learns that it can reach A through S4. They don't have entries for B, and so they flood the packet. And B ends up getting, the packet ends up getting to B, right, which is where it was supposed to get to. So now, if B wants to reply to A, it can just follow the table entry straight back to A, right? It doesn't need to flood it anymore because there's now table entries to A. Moreover, as this packet progresses from right to left here, it's like leaving behind table entries that point to B using that same process, right? So the next time A wants to send a packet to B, it doesn't need to flood it either, right? It can now send it directly using those table entries straight to B. So the big problem here was what? Cycles. Yes, the big problem here is cycles, right? As we learned last time, we saw the video, when you have loops in your network, flooding runs you into some problems. So, I said our previous solution for flooding doesn't work in this case, and that I would come back to it. So first, I wanted to point out that the decision of whether, to flood or not is like made on a switch-by-switch basis, right? It's not like a given packet is like, going to be necessarily flooded across the entire network or sent sort of point to point across the entire network. It's every time it gets to a switch, you look at the table. If there's a table entry, you just send it to that neighbor. If there's no table entry, you flood it, right? And so here I said with some pseudocode, and who am I kidding, this is Python, of basically the algorithm for a learning switch, right? So a packet arrives from some neighbor, which we'll call the previous hop. And the first thing you do is learn from that neighbor, right? You've got some table. You use the source address in the packet to pick the table entry. And you set the next hop to be the previous hop, right? If you're trying to go to that address, then you use the hop that you got this packet from. You also set a TTL so that these things eventually time out and you can learn new ones, which you might want to do because the topology might change or the host might migrate from one place to another or something like that. And next, we do this forwarding part where if the destination, if we have a table entry for that destination, then we look up the next hop. If that next hop is the previous hop, meaning the table entry is telling us to send the packet back the way we came, we don't do that. We just drop the packet and stop there. Because, of course, if we sent it back to the switch that just sent us the packet, they're probably just going to send it right back to us, right? They had just sent the packet to us in the first place, so we don't want to send it back. Otherwise, we'll use that next hop. We'll forward the packet there to that next hop. If the destination wasn't in the table, then we're going to flood the packet to all the neighbors except the one that we just got the packet from. So is that pretty clear what this algorithm is? All right. So back to this. I said our previous solution for dealing with loopy topologies doesn't work in this case. So first question, what was our previous solution to dealing with loopy topologies and flooding? This was in the context of how we flood in link state. We need to spread that local information globally in link state, and we do that by flooding. And so how did we solve the loops in the flood problem for link state? Sequence number, right? Like, we have this rule, basically, where, like, the first time we see this packet, we flood it. If we see it again, we don't. And we know that we've seen it again because, basically, for each router, we're keeping, like, track of its highest sequence number, which it increments every time it sends a packet, right? So if we've seen a sequence number, if we see a packet with a lower or equal sequence number to the most recent one we've seen, then this is an old packet. If the sequence number on the packet is higher than the most recent one we've seen, then it's a new packet, right? But this doesn't work for this case. So why not? There's probably several answers here. Anybody have an idea of why this wouldn't work for this case? So the senders, in the case of link state, who was sending the packets? The packets that were flooding. Who originated those? Yeah?
So is it because the sequence number should be like incremental on the router, not packets, like if it's packets is too much?
I think you're almost there. So is it because the sequence number should be on the routers and not on the packets, and maybe a scaling problem of some sort? So in link state, we were the problem we had were these looping route update messages, right? So who sent the route update messages? Was it a host? See some shaking heads, thumbs up if it was a host. Thumbs down if it was something else. All right, so what was it? It was a router, right? The router sent them. And so you're keeping track. Every router needs to keep track of the sequence number for every other router. Now, in this case, we're not talking about routing messages, right? This is powered by data packets, right? So who are the sender of these packets? Hosts, right? Potentially every host, right? Like in your network, how many routers are there? I don't know, some number. How many hosts might be sending data through your network? Potentially a very, very, very large number, right? You probably can't keep track of all the sequence numbers for every host. You also have this problem that data packets don't necessarily even have a sequence number, and it's too late to do anything about that now. Yeah?
Well, I know that for sure in real internet they put TTL on packets, but if in real internet things move, that packet will die off after a certain TTL.
Yeah.
So we just use that here as well.
Yeah, so could you do that? And to some degree, that would probably just happen, except, again, it gets to sort of the, and for reasons that we'll kind of get into earlier, but these might be L2 packets, right? And L2 packets don't have a TTL, at least at this point. So there is that. But you're right, you could potentially do that. You could say, here's a new version of the L2 header that has one. And so that would work. Some of my research is actually in this area, and I use that amongst other approaches as part of it. So there are things that you could do. Yeah, so there are definitely alternate approaches, but in general, the one that we used for routing doesn't work for link state.
Well, yeah, those are TTLs in the router. This would be a TTL stack.
Right, I'd say it's a different approach. The one that we used for link state doesn't work. You could come up with something else, absolutely. But the solution that was sort of decided upon for this, for various reasons, is to disable links in the network until there are no loops, but you're still connected. So essentially, you turn the network into a spanning tree, just getting rid of all the loops. Once you do that, you can flood safely, right? Because you can flood safely on a network with no loops. So does that make sense, what the approach is? Take your network with loops, disable links until it doesn't have loops. And so to do this, we have this protocol, imaginally called the spanning tree protocol. And so how it works is it basically does three things. The first one is it finds least cost paths to every switch, from every switch to the root. And then it disables data delivery on all of the links that aren't on a path to the root, a best path to the root. And then when the tree breaks, it starts over. So looking at these in some more detail here, the first step, we find least cost paths from every switch to the root. And this should probably sound pretty familiar, right? Like, as we talked about in the first routing lecture, essentially we're forming these trees to every destination when we're doing destination-based routing, right? So we already have talked about a couple algorithms or protocols for solving this particular problem. And essentially it turns out that the spanning tree protocol ends up being incredibly similar to distance vector. The big difference is that it only makes a single tree, right? When we talked about distance vector, we had a tree basically rooted at every destination. And now we just have one single tree. In a bunch of our examples, we were only looking at one destination at a time, just because it was the same for every other, the same process for every other destination. But in this, there literally is just one destination. And that destination, that root of the tree, the spanning tree that we're constructing, is basically, it's the switch with the lowest numbered ID. So every switch has a sort of intrinsic ID, and you pick the root by just using the one with the lowest one. And so it turns out that you can basically, with a slight tweak to distance vector, you simultaneously both get best paths to the root while also finding the lowest numbered switch to use as the root. So you actually do those two things at exactly the same time. So in detail here, the algorithm looks kind of like this. All switches start out by thinking they're the root. As far as they know, they have the lowest ID. They advertise essentially like a route to themselves, to all their neighbors, just like we did in distance vector, right? And so, that message says something along the lines of, the root is, and at the beginning of time, they just say, my own ID, and I can reach it in 0 hops because it's me, right? So everybody starts out by saying that to their neighbors. And then when you receive one of these spanning tree messages, which is like a route in distance vector, like a route advertisement, the first thing you do is compare the advertised route to what you think the route is. If it's smaller than what you think the current route is, the advertised one is smaller, then that's a better route, right? Because you're trying to get the smallest one. So now that's going to be your route. If it's bigger than what you think the route is, then you ignore it, right? Because that's not what you're looking for. You're trying to find the smallest route. And if it's the same, right? If the advertised root, this advertisement comes with the same root as you think the root is, then you essentially just do the normal distance vector type update, right? Where if it's smaller than the one you have, then you choose the smaller one and keep track of which neighbor to use. One little difference here is how you break ties, right? If you have two neighbors that are telling you the same distance to the same root, then you break the ties by preferring the advertisement from the neighbor with the lower ID. So you never end up actually having a tie. You can always end up saying, this one is closer. Does that make sense? Yeah.
So, I think the situation where you have like two switches, one of them is the actual like root, and one of them takes this root from just the beginning.
Yep.
So these two exchange, so this break ties, how do we actually, can you explain to me like how we actually know that the first one was the actual root? Because both of these think that they're at the root.
They both think they're at the root, and they both tell each other their ID. So if you're one of the switches, I'm one of the switches. I say, I think the root is 0, and the distance to it is 0. And you say, I think the root is 3, and the distance is 0.
Based on that, my ID is 3.
Yes.
Okay. And so that is just based on the fact that, like, okay, so, like, human will say in the system, like, okay, this has to be, like, ID 0 on the actual root. That way, the ID. Like how do you decide that?
Right. So how do you decide where the root is, sort of, right? And so one answer to how you decide where the root is who cares? It doesn't matter. All you're looking for is a tree. Right? So which actual node happens to be at the root? Maybe it doesn't matter. In practice, so to some degree, every switch, the way it works on modern on switches for the version of spanning tree that's deployed is every switch actually has a number of addresses, Ethernet addresses, which are like kind of burned into the hardware when it's manufactured, and those are all unique. And so you actually just use like the lowest one, and so that ends up being your ID. But essentially, just intrinsically, every switch has an ID. Operators also, the way the protocol works, can modify it. So they can kind of override it if they do decide that some switch is better than others to act as the root. But this is actually a management problem. If you, as an operator, say, oh, I want this switch right here to be the root, right? What happens when that switch fails? Well, that's not the root of any tree anymore. It's going to be something else. And so did you plan for that? If you've planned something saying it's vital that this switch be the root, and then there's some sort of failure and it's not the root anymore, how far ahead did you plan? So, yeah. Any other questions on what this algorithm looks like? And we'll walk through some examples. Yeah.
So, I guess the conditions on receiving a route from the neighbor, when it says if it's smaller than current, is that referring to the distance or the ID?
If it's smaller than current, it's saying compare the advertised root to what we think the root is. So it's comparing the IDs of the root. Yeah. All right. So when things update, you send a triggered update so all your neighbors know that your root or your distance to it has changed. And another difference from the distance vector that we talked about, in the one we talked about, every switch was like periodically telling its neighbors, advertising to its neighbors. Spanning tree, just a little detail is that it works a little bit differently. Only switches that think they're the root actually generate these spanning tree messages, these sort of like periodic updates. And the other switches just forward them. And so there's only sort of like one source of these things. But it has sort of the same effect. If ever a link goes down between two, they'll stop being passed from the root through those links. So the second step was to disable data delivery on every link that's not on a shortest path to the root. And so we're going to look at the algorithm by which you decide that. And I want you to kind of remember that you can think of every neighbor as either being closer or farther from the root than you are. there are no ties, right? Like, they may tie in terms of the distance, but you can always break that tie because you then compare the IDs, and the IDs are always unique. So you never really end up with a tie. You can always say, if they have the same distance, the one that's closer is the one with the lower ID. So to do this, each switch basically enables the link that's along the best path to the root. You're definitely going to turn that one on. And then every other link that's to a neighbor that's closer to the root than you are, you're going to disable that one. So you only have one link pointing towards the root. Every other link you have is pointing to a switch that's farther away from the root than you are. And so you don't do anything about those ones. You let them decide, because they're going to decide, you're going to be nearer, and so they're going to make the decision about which one to enable or disable. You also enable all the links to hosts. And, any link that's not to a switch. And so how do you know which links don't lead to other switches? Yeah? Well, you don't necessarily have any static routes with, we haven't seeded this algorithm like we do with the other one. So good thinking, but not in this case. Yeah? You never heard an advertisement from there, right? Because they're not participating in the spanning tree protocol because they're a host. All right, so we'll do an example here. So here's a little topology. We're gonna have these gray dash links for unknown or indeterminate links. We're gonna use black for when they're enabled, and red messy links for when they're disabled. So S1 is gonna be the root here, right? Lowest ID. So from S1's perspective, this link here, enabled or disabled? Thumbs up, enabled? I see some thumbs up. Yeah, it's enabled, right? This is along the best path to the root. Nope, sorry. What am I thinking? I was thinking from S2's perspective, which is not what it says. So this link, S1, S2, from S1's perspective, this is pointing away from the root, right? Like S2 is farther from the root because S1 is the root. Every link is going to be farther away, right? So it's going to be in this unknown, indeterminate state, right? We're not going to decide on links that are pointing to routers that are farther away from we are. All right, so what about this one? Enabled? Disabled? Yeah, disabled, right? Like it's the exact same thing as the other one. Like this is not towards the root. All right, S2's perspective. This is what I was thinking last time. So what about this link? Enabled? Enabled, right? Because this is on the best path from S2 to the root. How about this one? Yeah. No, right? Like, we're not going to deal with that one because it's pointing to one that's farther away. How about this one? So, right, like, this one is the same distance away from the root, but it's got a higher ID, right? So it's pointing away, so we're not going to decide on this one either. Yeah? S4 is the same distance. Like the distance that S4 advertised is the same distance, right? S4 is not advertising the root. We're going to assume that they actually know who the root is. They've already figured out who the root is, so it does know who the root is. Sorry. So this one, this link from S3 to S2. Enabled? Yeah, right. So it's it's closer to the root than S4. S4 is also closer to the root, right? But we've broken the tie between S2 and S4, right? These both kind of look like the same, except we've broken the tie by going with the lowest ID. Yes.
When you break ties, you look at the ID of the
No, you're looking at the ID of the one that gave you the advertisement. So, the one that like gave you the route. So you're looking, like if you get an advertisement from S2 that says, I think the route is S1 at a distance of 1, and you're going to get one that's from S4 that says, I think the route is S1 with a distance of 1, it's the 2 versus 4 that breaks the tie. So that one is enabled. This one here, it's also closer than S3 is, but it's not on the shortest path, so we disable this one too. This one we disable. All right, this one here, is it on the shortest path from S4 to the root? It is, right? Yeah.
Sorry, I'm so confused about the reason that you say that you don't have to link from S2 and S4. Could you go back and explain that again?
Yeah. So from S3's perspective, right, both, like, if you look at distances, like, pure distances, S2 and S4 are both sort of telling you that they're like one hop away from the root, right?
Sorry, I meant the link from S2's perspective to S4.
From S2's perspective to S4. Sorry. Where is that? Yeah, S2's perspective to S4. So in that case, right, like S2 and, so S4 is the same distance as S2, right? They both are one hop. But we're going to say it's farther because we break the tie. We're saying S4 is greater than S2. Therefore, we decide that it's on the far side.
Wait, I don't understand, because isn't S4 2 hops away from the root through that path?
Not through this path, right? S4 is talking about from its perspective, like it has heard the advertisement from S1 also, directly from S1. So S4 knows that it's one hop from S1.
Oh, okay.
Right, we're assuming that they've all actually figured out who the roots are.
Right, so then why would there need to be a tie break, is what I'm saying?
There is a tie break only in order to decide whether you're going to disable this link or not. Because our rule for disabling, the rules for disabling links are on here. And so it's like, you enable a link if it's on the best path to the root. And you disable it if the other neighbor is closer to the root than you are, but not on your best path to the root. Right? And so this one, if it was, S1.5, we would consider it to be closer because it's the same distance, but then we break the tie between them. Does that kind of make sense? Yeah, it's a sort of confusing algorithm, but yeah. Yes, S1 was chosen to be the root because it's the lowest ID. All right, so from S4's perspective, S1 is on the shortest path to the root, so it's going to be enabled. So from S4's perspective, this link S3 and S4, what do you do with it? Is S3 closer to the root? No, it's not, right? So we're going to ignore this one. It's already disabled, but we're just going to leave it alone. S4's perspective, yeah.
So when you say disable, do you mean that you won't set packet over that route, or do you set shut off?
Right. What that means is essentially data traffic should not be flowing along that link. So like S4, S3 won't forward traffic along that link. It'll instead forward to S2. Yeah, so what about S4? to S2. Is that the shortest path to the root? No, right? That was through S1 directly. Is S2 closer to the root than S4 is? Yes, right? Same number of hops, but smaller ID. So it's closer to the root. So what do you do with this one? Enable? Disable? Yeah, you disable this, right? And so now you take these links that everybody has disabled and remove them, and you get this spanning tree. Yeah?
I think the same with this question. You said it's the same distance, but there's like one path is only one edge and another is two edges. Do you assume that sending to yourself consumes one edge? Or?
Yeah, so you're not actually considering like the distance as if you sent to them. You're just considering where they are forward or behind you in this sort of like absolute order.
Yeah, but shouldn't you know that if you send to them, then you're consuming one hop?
Yes, I mean, that's true if you were to send through there, but you're not actually sending to them, right? You're just deciding which links to enable or disable. So you can just go by what their distance is from the root versus your distance from the root.
Then, so for this case, why are you disabling S4 to S2 from S4's perspective if S2 has a lower ID?
It's got a lower ID,
Yeah.
so it's towards the root, but it's not on the best path to the root. So you enable the one that's on the best path, and you
You're trying to find the path, which means you don't know the path yet.
In this case, we're assuming that they've decided, they've already come up with what is. I mean, that's just distance vector essentially, right? They've already decided what the best path is. Now we're just trying to figure out which links we're enabling and which ones we're disabling. Right? That's kind of a separate part of the problem. The first part of just sharing the updates, telling them, advertising, etc., right? That's the normal distance vector part. This part is the second stage where we're taking that information that we got and we are deciding which links to enable and disable.
But if you know the best path, why don't you just disable links that are not that path?
Well, so like if you're at S2, right, then the best path to the root doesn't include S3. So if you just use the thing of I'm only going to disable things that are on the best path, then S2 would say, okay, well, S3 isn't on the best path either, so I'm going to disable that. But you don't want to disable that because that link actually is useful, right? Because S3 needs that link. Does that kind of make sense? Other question? Yeah.
Can you say again what is the relationship between disabled and no?
Yeah, so essentially, from a given switch's perspective, it's only going to decide on ones that are closer to the root than it is, and it's going to leave the other ones. It's not going to make a decision on those ones. The ones that are further away will make a decision on those ones. So, like, from S2's perspective, this link to S3, it's not its responsibility because S3 is farther away from the root than it is. Right?
So S2 marks S3 as unknown, like S2 as
Yeah, it doesn't even have to mark it as unknown. It doesn't do anything. I mean, it leaves it enabled and then lets it be S3's responsibility to disable it.
So at what stage does S3 and S4 get disabled?
At what stage does what get disabled? At S3 and S4? I mean, they're doing it kind of on their own, right? Like they're deciding on this asynchronously. So just whenever there's actually essentially a timer where after they figure out the paths that they think are the paths to the root, they essentially say, okay, I've now believed this to be true for a few seconds, that this is the best path to the root, et cetera. And then after that goes off, then they disable the links that they're going to disable. Kind of makes sense? You can come to office hours. We can discuss it to your heart's content. All right, so going to move on to step 3 here, which was, when the tree breaks, when a link fails, you start over. And so basically when your route expires, right, like when you haven't heard a spanner tree message from the root for a while, then basically you just pretend you're the root again, advertise as if you were the root again, and this basically will just start, another process of trying to converge and find the root. Everybody will tell their neighbors, and you will hopefully find new links to enable and disable to get a new tree. So to sort of sum this up, spanning tree protocol is basically distance vector, except you're always figuring out like the root to a single switch, which is the switch with the lowest ID, and you don't use those roots that you found directly. Instead, you use them to figure out which links to enable or disable. And after disabling links, your topology is logically a tree, and your learning switches can flood freely on that tree, not having to worry about there being loops. So spanning tree protocol learning switches are generally only used in layer 2 networks. In layer 2 local networks, bandwidth is usually plentiful. The number of nodes that you have to deal with are relatively small, so flooding is feasible, right? You wouldn't want to flood on the entire internet. Flooding lets you reach destinations like without having routing information at all, right? You actually don't need to have any table entries in order to reach from one host to another. But they're nice, right? Because they let you take direct paths and not use links that you don't need to use to get from one place to another. Flooding lets you sort of find hosts. You don't need to have this statically configured routes. Because, if you flood and the host is out there, the packet will reach it one way or another. And finally, once a switch has seen a packet from a host, it has a table entry for it, right, because it's a learned one. And, if all switches see a packet from a host, then there's not going to be any need to flood anymore. Any questions on spanning tree protocol? Yeah. So what if some switches think that you need to find a new tree and others don't? Yeah, so it basically works out, right? I mean, when we were looking at distance vector, it's this like really asynchronous protocol, right? If you kind of, if you reset a switch in the middle of a distance vector network, it'll send updates to its neighbors and it'll get updates from its neighbors, and eventually they will sort out a new path. So you can certainly have, points of like where you need to converge in spanning tree protocol, right? Where different switches have different ideas. But, as we saw, the distance vector algorithm, and as you'll see in the project with any luck, this sort of distance vector approach does eventually stabilize on the correct answer. Yeah? So in this, we're assuming that we know the root, but I mean, we're just making one up essentially, right? Like how it's decided isn't important. And so, right, in distance vector, you have a destination, you have however many destinations, you essentially have like static routes or other routes that are propagating, right? Hopefully like one for every host, or something that will cover every host. And in this, you only just have the one, but it doesn't really matter because you don't really care about forwarding to any particular node. All you care about is that you're only forwarding on a tree, right? The actual destination is irrelevant. You don't even necessarily forward following the path to that destination. You forward following the paths that you've learned. We just needed to have one node that we decided was going to be the root of this tree. Yeah? Is the root always the smallest idea? By default, yes. It can be overridden, but in general, that's the way that it's found. Yeah?
I thought with spanning tree, we assumed that all nodes assume
Yeah. How does that happen? So everybody starts thinking they're the root, and then somehow we end up narrowing it down and finding the one that's actually the root, right? And the way is basically, it looks very much like the distance vector update. When you get an advertisement, they tell you what they think the root is. And you compare it to what you think the root is. And if what they said is lower than yours, then you use theirs. If it's higher than yours, then you stick with yours. Yeah.
So in the example we did, we assumed S1 was a root, right?
Yeah.
So I just said that S1 thinks they're the root, and then we went all the way down to we didn't do that with the example.
Right. So the example, we started knowing the root, and I guess I should have been clearer about this. We started partway through, right? There's two stages to this algorithm. Well, I mean, there's actually three, right? But the first part was we find the least cost paths from every switch to the root, right? That's the first part of spanning tree protocol. And this is the part that's like just like distance vector, right? Where you just find what these are. The second part is where you disable the links that aren't on those shortest paths. And so the examples that I was doing were examples of the second part. There, once you've already spread this information around, you've found what what your next hop is along on the path. How do you know which links to enable or disable? And so that's what this was an example of, is that second part, where we've already figured out our best paths. We're just figuring out which links to enable or disable. Does that maybe clear some things up? I think you were not the only one with this misunderstanding, so my bad. Yeah.
Are these two phases distinct, or can they mesh over?
They can definitely be meshing over. I mean, they're certainly not synchronized between different switches, right? Yeah. So the actual way, there are actually like a few states that they go in. Like, right now I'm just trying to decide what my paths are, and then after it does that for a while, then it switches to another state where it's going to enable or disable things. So it's a little bit tricky, but not super important. But they can happen at once, certainly across different switches. Yeah. Why would you use a? Yeah, so why would you use not a minimum spanning tree? And so what's the difference between the two? Yeah, so if you have edges that actually have weights, right, then you can choose a minimum spanning tree. If you don't have edge weights, then the two are equivalent. Right, every spanning tree is a minimum spanning tree. And so in the original version of spanning tree, it didn't include weights. Modern versions actually do, but we were kind of ignoring them. So the modern versions do actually come up with not necessarily a minimum spanning tree. I think they do find least cost paths to the root, but I believe, it's been a while since I thought about this, but I think to have a minimum spanning tree, you actually need to choose the root well. Right? And in this, we don't have any algorithm for figuring out what the best possible route is. We pick the route kind of at random and then can just get the best path to that route. So that's kind of, I think, the answer is we don't have a good way of figuring out what the ideal route is. All right, I'm going to move on from this. Questions on Piazza, office hours? All right, final thing about spanning tree protocol. Spanning tree protocol was invented by Radia Perlman, who also worked on ISIS, which is one of the link state protocols that we talked about. And she tells this story about the development of spanning tree protocol, which goes something like this. Her company needed a solution to the problem of loops in its network. The problem they were kind of facing was, it's really easy for an operator just like plug in a cable in the wrong place and create a loop in the network and bring down the network, right? And they were struggling with figuring out this. So her boss gave her the problem on like a Friday before he was going out of town for a week. He says, I'm going to be out of town. Why don't you take a crack at this problem? And so she solved the problem over the weekend. So the whole next week, her boss was gone, and so she spent the entire time writing up the algorithm in the form of a poem, or as she calls it, an algorhyme. And so it goes something like, I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree that must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree. So, Radio Perlman's algorithm, LAN was referring to an L2 network. Mesh, she was talking about a network with a high degree of connectivity, lots of loops. And a bridge is sort of a dated term for a switch. So, spanning tree protocol. All right. Moving on to addressing. I'll also talk a little bit about how interior gateway protocols and exterior gateway protocols interplay. All right, so a number of people asked this question. How do routing and forwarding scale to the size of internet? Can you actually have a table entry for every host? And how long would it take distance vector to converge when it's sending all these messages? It has to deal with, speed of light delays. Can a link state router really build a graph of the entire network to run Dijkstra's algorithm on? And how long would it take to run Dijkstra's algorithm on a graph of the entire internet, right? Et cetera, et cetera. And so, I've mentioned that intradomain and interdomain routing protocols use, different algorithms and work kind of differently. And we've mostly talked about intradomain so far. So, maybe the magic of routing, maybe the exterior gateway protocols that do routing at the level of the internet have some magic. They scale much better for some reason. But it turns out that the magic of scaling is actually mostly in addressing. So, we're going to talk about addressing, and specifically about IP version 4 addressing. IPv6 is pretty similar. I'm not going to talk about it too much in this class. And without talking too much about the details of BGP, we're also going to talk a little bit about how intradomain and interdomain routing interact, at least conceptually. I'm not going to say anything about L2 addresses today. All right, so starting with a little internet history. This is a bit simplified, but I'm hoping to get the basic points across. Remember, the internet is a network of networks, right? So here we see that network of networks, the internet. And here we can see the inner networks too, right? Sometimes we call these individual networks domains or autonomous systems. And so note that this really naturally leads to this sort of two-level hierarchy, right? And hierarchy is one of our major tools to address issues of scaling, right? In CS and in routing, but in everything. So one can imagine a scheme like this, where every host has an identifier. And that's pretty similar to everything we've been looking at so far, right? A host has a unique identifier. But networks also have identifiers. And so an address could look something like network.host. So this host here, you could say it was 3.7, right? It's in this network 3, and it's the 7th host, and the one next to it could be 3.6. And so thinking through the implications for routing here, the border routers doing interdomain routing don't need to know anything about host addresses. They only need to know about how to reach the other networks. And so this limits the number of table entries used for forwarding, right? At R9, everything going to an address starting in 4 goes to R6, right? The star is like a wild card. So anything 4 dot whatever goes to R6. And this also limits whatever other routing state you might need, right? If we don't use link state at the interdomain level, but if we did, right, we wouldn't need a graph including every host. We just need a graph including these domains. This also limits churn, right? If a link goes down in some domain, the interdomain routing doesn't necessarily need to know anything about it, right? It doesn't change how the routing between the domains is done. So the number of routing messages that you care about goes down. This also helps you scale, right? So if you assume that there are many more hosts than networks, then this is a big improvement on scaling. So what about the internal routers? Well, they need routes for all the hosts in the same network, right? So like looking at R4 here, it needs to have routes for 3.1, 3.2, 3.3, etc., right? So this scales with the number of hosts in the network. And it needs to have those routes to other networks, right? Like if R4 gets a packet to, 1.6, it's going to need to know something to do with that packet, but all it needs to know is send it to R9. So how does that happen? We've talked about how, we sort of seed our distance vector and link state protocol with like static routes, right? But these are the routes that we care about, right? These are the same routes the interdomain protocol got that tells us how to get to another domain, right? So essentially, we can use those to seed the routing table at R9 with those interdomain routes, and then the intradomain routing protocol distributes them the same way we distribute any route in the interior gateway protocol, right? The same way we would have distributed static routes. Those will propagate, telling you, oh, okay, well, they started at R9, and so they'll learn that the best path is back through R9. So that lets us create table entries for the 1, 2, and 4 networks throughout R3. So does that make sense, what I'm saying about how these interact? Like R9 is communicating with other exterior, border routers, figuring out what the interdomain route should be. And then it's basically using the interior gateway protocol to propagate those to all the routers inside network 3 here. All right. So also note that R9 is also doing internal routing, right? It's going to get packets from outside that are going to go to one of these 3.1 or 3.2. So it also needs to have routes for the other hosts inside R3. I just didn't show them. So the total state scales with the number of hosts in this network, right? We don't know anything specifically about hosts in other networks, plus the number of other networks. Does that make sense as a starting point here? So a final note on this is, you actually, for this network, you don't even need to know about the individual routes to the other networks. In this case, there's only one way to get to any network besides 3. And so you could have a default route that just matches on anything and says, if you don't match one of these 3 dot whatever ones, then you're definitely just going to head to R9 and leave this domain, go somewhere else. R9, of course, still does need to have those routes for all the different networks. Right, because it needs to know, is it sending them to R6 or R8 in this example? So does that kind of make sense? What's going on there with this kind of 2 levels of routing? You're routing between networks, and then you're routing between hosts within each network. And the 2 are getting kind of spliced together. So I want to point out here that addresses aren't assigned totally randomly, right? There's a structure to how we're assigning addresses. All the hosts that are like in some sense close to each other on the same network, their addresses all share something too. They all share the same network part of the address. And we're leveraging this structure in order to make routing and forwarding scale better. We do this sort of thing all the time. We use these structured addresses, right? Like Soda Hall 417 is a much easier way to work with my office number than like if every office just had like a unique number. And I said, I'm in office 982,403,000. And you're like, okay, where is that? Is that in this state? I have no idea, right? So you have this sort of 2 levels of addressing there. This also explains why hosts don't generally participate in routing protocols, right? Because, a human had to decide how to allocate these networks, how these things grouped together. So they had to type in at some point how that worked. Your computer doesn't have an IP address that follows it around wherever you move your computer. Instead, when you move your computer to a different network, it changes its address to an address in that network. So it's sort of like, when you move apartments, your address doesn't go with you. You switch to the address where you moved. So the way that happens automatically in IP is through a protocol called DHCP that we're going to talk about later in the semester. So to recap here, we're assuming that addresses have two parts, a network part and a host part. And the border routers run an EGP routing protocol to figure out the routes between networks. And the internal routers are running IGPs to figure out, the host routes for the hosts in that network, and also to propagate the network routes that it learned from the EGP. This scales a whole lot better than flat routing. The border routers don't see the churn inside all the networks. The internal routers don't see the churn in other networks. And routers only need state for the hosts in their network and for other networks themselves, not the hosts in them. Does that make sense? Thumbs up? Kind of makes sense? Thumbs down? If anybody, no? All right. So that's basically how addresses worked in the early internet. I want to, before we dig into how things have sort of evolved, just take a step to look at IP addresses themselves in a bit of detail. And so first off, they're 32 bits long. Every host has a unique one at a particular time, more or less. In the early internet, those 32 bits were broken into an 8-bit host part, an 8-bit network part, and a 24-bit host part. They were always broken down like that. And when an organization wanted to get on the internet, they would get their own network part. For example, Apple got 17, and that's still true today. Any IP address starting with 17 is Apple. So this is all still true right here. They're still 32 bits long. This stuff has gotten a little bit more complicated. We'll talk about that in a second, but first let's just talk about how you write IP addresses. And so you could have just represented them as like a big old integer, right? It's just a 32-bit number. And in fact, on a lot of systems, you can still do this. You can, ping or open a web browser and just enter a number, and it'll work. But it's much more common to write them in this form that we call a dotted quad or a dot quad. And basically, you just take each of the 4 bytes in this address, you convert it to decimal, you throw dots between the 4 of them, and that's what an IP address looks like. In the old internet, this one would always be the network part. The rest would always be the host part, right? And so, like I said, if they start with 17, they are still to this day Apple. And you can, in fact, write them also with 1 dot. This is a weird way to do it, but you can do it. You can write like a network number, and then a dot, and then just a 24-bit number. All right. So, thinking about how this has evolved, you may have noticed that only 8 bits were allocated to the network part. So how many possible networks could there be? 256. So 256 networks. That I guess that seemed like enough at the time. I think they were probably wrong. So it became clear that we needed more networks pretty early on. And so what they did was invent classful addressing. And so basically, it breaks up the bits in the address in different ways, depending on the prefix here. So every address where the top bit is a 0, the top 8 bits, including that 0, so 7 more bits, are the network number. And luckily, when they made this up, they hadn't gotten to network numbers higher than 127, so all of the old ones still work. That's why Apple got 17 and still 17, or why that's possible anyway. So that you have, this essentially 8-bit network number and then 24 bits worth of hosts. So you have 126 networks. They each have about 16 million hosts. Class B is any address where the first 2 bits are 1, 0. And so the rest of that is the network part. And so you end up with about 16,000 networks, and they all have about 65,000 hosts. And Class C, if it starts with 110, then the rest of the first 24 bits are the network number. After that is the host. So you have about 2 million networks that have about 254 hosts each. 254, not 255, not 256, because the 0, like all the bits 0, all the bits 1, those are reserved for different reasons. So it's always like, when you have a network of some size, you subtract 2 to find the actual number of hosts you could have. So now we have a lot more network numbers available, right? There's like over 2 million here, right? There's 2 million just of the Class C networks, and then you've got the other ones. There are some other classes too, but these are the 3 big ones. So when an organization wanted to get on the internet, they basically figure out how many hosts they think they're going to need, and then they get a network number that's sort of like appropriate to their needs, right, to one of these sizes. This plan ran into a problem of its own. So the first one is that the sizes of the classes, they're nice, they fall in these like byte boundaries, right? That's nice, it makes them easy to read. But like, they're not super useful sizes, right? Class A, you got 16 million hosts, right? Like, not a whole lot of organizations have 16 million hosts, right? Class C, on the other hand, is like way too small for a lot of organizations, right? It's only got 256 hosts, right? There's probably 256 hosts in this room. So, the best option for a lot of people was Class B, and there aren't that many Class B networks, right? There's only like 16,000. So it's sort of the way they broke this up was not great. And, there's another thing here. The second problem is sort of hinted at by the fact that they, were worried about running out of Class B networks. The fact that they were worried about running out of Class B networks, implies that they were getting close to having 16,000 networks, right? So at the interdomain level, the interdomain routing, you are routing with tables of, like 16,000 entries. And this was starting to be taxing for the routers of the day, right? And the whole point of the way we broke up addresses was to like make the interdomain routing table smaller. And they were certainly smaller, but they were getting too big. So number of interdomain routes was going up. And so this was really happening. A graph of the growth of interdomain routes by year looked something like this between 89 and 94. So it was growing. It was growing super linearly, right? Like, look at 1993. It almost doubled just in the year 1993 here. And look at where it ended up, at like 15,000-ish, right? Remember, there were 16,000 Class B networks. So if most of these were Class B networks, then we'd already spent most of them. And of course, if we run out of Class B networks, what are we going to do for an organization that needs more hosts? We're going to give it a whole bunch of Class C networks, right? That's how we're going to make up for that? Yeah.
I don't quite understand how the classes work together. There are companies choose one of the classes, then your network is sort of, shorter. Then how are you going to send to other companies with longer networks?
The addresses are all the same length. So the question is, how do you, interact with ones with different ones? The addresses are all the same length. It's just how many bits you use for the network part, right? So basically, if you have a address that starts with a 0, right, then its network number has to be less than 128, right, in order to fit in that remaining 7 bits. And so networks like that have 24 bits worth of hosts, right? So you can just tell by looking at this address how many, what the network number is and what the host part is, the bits associated with the hosts.
So ultimately everyone would want Class A, but when it runs out, then you have to choose Class B.
Well, I don't know if everybody would optimally want Class A, right? I mean, it doesn't really matter. What matters is, do they have enough, do their hosts fill it, right? I mean, what you really want is you want to probably choose you want to conserve the bits, sort of, right? If I have 10 hosts in my company, then giving me a Class A would be a huge waste, right? There are, roughly 16 million hosts will fit in a Class A network, and I'm going to use 10 of them. Nobody's going to use the others. So you would much rather give me a Class C network. not sure that's answering your question, but I think it'll have to wait till next time or office hours or something, because I think, no, we still got time. Yeah, so is that answering your question? I'm not positive I'm understanding the question.
Yeah, so if you have like a long network part, then it means that your company's network length is longer. So it's for your own company, or when you're communicating, you're using the network?
So it's really just a number, right? I mean, all the addresses are 32 bits. It's just how do you want to break up the bits between a host part and the network part, right? If you know, one solution to this problem would have been, say, you know, if we made addresses 256 bits, right? Then 128 bits of the address could be for the network, 128 bits could be for the host, right? Like, surely that's enough for the number of networks that you could possibly have and the number of hosts that you could possibly have, right? If you had that many bits to work with. Is that believable? Like, 128 bits gets you like the number of atoms in the universe or something like that, right? You're not going to fill up that many hosts or that many networks, right? So if you wanted to spend the bits, you just have a giant number for the network, giant number for the hosts, right? But they didn't want to do that. Instead, they had 32 bits to work with. And so, you know, sort of what they did is they started with this sort of static thing, and they said, okay, 8 bits, 8-bit host number, 8-bit network number, 24-bit host number, right? So that was where they started. But what they found was, well, that's not enough bits for the number of networks we have, right? So they could have said, well, okay, we got it wrong. Instead, we're going to have 16 bits assigned to the network, 16 bits for the hosts, right? But, well, now we only have, you know, 65,000 possible networks, and each network can only have 65,000 hosts, right? Like, and if we have some network that only has 2 hosts, then we've just wasted almost 65,000 addresses, right? And some network is probably going to want to have more than 65,000 hosts. So this was an attempt to sort of say, well, some networks are going to be one size, other networks are going to be another size, other networks are going to be another size still. And so we've just sort of broken up the space so that the network number sort of determines which of those classes of address you have. The low network numbers are going to say you have a lot of hosts. The medium ones are going to say you have this intermediate number of hosts, and the large network numbers are associated with smaller number of hosts. Does that kind of make sense?
Yeah.
Okay. If it doesn't, we'll come back to it. Let's talk about it in office hours. Or everybody complain on Piazza, and we will go through it. All right. So where were we here? So they needed a new solution here, right? Because of the problems with these two problems with classful addressing. And so that was this thing, CIDR, which is classless interdomain routing. And this is still what we use today. This is what we've used since the early, mid-90s. And it solved both of these problems the same way by doing 2 things. And so first of all, it introduced this hierarchical process for the assignment of addresses. And secondly, it gives up on this simple notion between like a static assignment between the number of network bits and the number of host bits. So starting with this hierarchical assignment of addresses. You know, like I mentioned earlier, it used to be that when you wanted to get your organization on the internet, you would go to ICANN, or at the time it was probably IANA. ICANN is the Internet Corporation for Assigned Names and Numbers. IANA was a sort of its predecessor, which is the Internet Assigned Numbers Authority. And they're the people who kind of are in charge of addresses and port number assignments and that sort of thing. And so if you want to get your organization on the internet, you would go to them and say, I want a network number. And they would say, okay, here's your network number. And so under CIDR, this got delegated in this hierarchical way. And so it started with ICANN taking a bunch of the unused Class C networks, a bunch of the contiguous IP address space, and giving them to these organizations called RIRs, or Regional Internet Registries. And so there were 5 of them. I think there's still 5 of them. ARIN is the American one, and they are responsible for IP address assignment in mostly the US and Canada. AFRINIC is Africa. APNIC is Asia Pacific. LACNIC is Latin America and the Caribbean. And RIPE is like everybody else, so Europe, Russia, the rest of Asia. And so ICANN gives some big chunk of IP addresses to them, and then they give out portions of those big chunks to large organizations like ISPs, and those organizations give out chunks to smaller organizations. So like AT&T might give out some chunk of their addresses to UC Berkeley. So running through an example here of how this might work, and this is completely made up. These numbers are definitely wrong, but just to kind of show you how it works, we'd say ICANN decides that the US and Canada should have 5 million addresses. So they need to give them 28 bits to get up to 500 million, right? So ICANN chooses the remaining 4 bits, the top 4 bits of the address, as a prefix. And they say 1101. I'm going to give that to ARIN, who's in charge of addresses for US and Canada. It says, every address you allocate is going to start with 1101. And ARIN then is responsible for delegating stuff to, companies in North America like AT&T. And so maybe AT&T wants 8 million of these addresses. So that requires 23 bits. So ARIN picks 5 more bits for the prefix. Right? And so, any address starting with 1101, 11001 is going to be an AT&T address. And AT&T might allocate 16,000 addresses to UC Berkeley. That's require 14 bits. So AT&T picks the next 9 bits of the prefix. And then it gives those to UCB, and Berkeley now has its own block with a prefix of 18 bits, and the remaining 14 bits it can use to assign to hosts. So every host at Berkeley would start with this prefix of 18 specific bits. Does that make sense? Each one of these below, is sort of, a subset. It's a part of the space of the one above it. These are inconvenient to write out in binary as a binary prefix, and so we often use this notation, which is sort of a variation of dotted quad. And so to do it, you just pad the rest of it with zeros so that you have another 32-bit number, like an IP address. And then you convert it to a dotted quad, right, which I've done for each of these. And now the problem is that from these just dotted quad, you can't tell, how long is the prefix, right? And so we use what's called slash notation, where we just write slash and then how long the prefix is. And so now this is what this prefix is actually referring to, right? It's these bits, and it's this number of them are significant. Does that make sense? Each of these allocations is contained in the one above. So besides slash notation, there's this other notation, net mask notation. Which is totally equivalent. It's just a different way of writing it. And so it's basically a bit mask of the prefix bits. So you just turn the prefix bits into 1, and then convert it to a dot quad. So using the same ones from before, 1101, this was the prefix. We just turn all the prefix bits into 1, convert that into a dot quad, and we get 240.0.0.0. And you just put a slash and put that after the dot quad of the network address, and that tells you the same information, right? It's just a different way of writing it. And so we can do that with all the rest of these too. That makes sense? Everybody clear on this? All right, then with that, I think we will resume here next time.
Bits that you return for prefix, is that determined already?
Sorry, the number.
Sorry.